Hi, welcome to Calculus. Today we are looking at section 10.1 in our book, Parametrizations of plane curves. So this is kind of interesting. It's definitely a little bit different way to look at graphs and some things that maybe can't even be represented as functions for us normally. So for instance, let's say we have this curve right here. As you can hopefully see in the video, it is definitely not a function. And so what we're going to do here is instead of having our functions be where our variable y is a function of x, or I guess you could do it the other way around, we're going to make the ordered pairs each a separate function. So let's take a look at what I mean. Definition: if x and y are given as functions, where x is a function of t and y is a different function of t, although I guess they could be the same, over an interval I of t values, then the set of points x, y is equal to these two function values, f of t and g of t. Defined by the equations is a parametric curve. So what we're going to do is we're just going to define all of our ordered pairs using two separate functions for each ordered pair. So for instance, let's sketch this curve given by x equal to t squared plus 1 and y equal to t minus 1. As you can see, I made a table of values so that I can try and figure out what this graph looks like. When in doubt, use more points. I like to say use enough points so that you know what the graph looks like. Here's a hint. If you change the mode on your calculator to parametric, it's like the fourth line down under the mode button. You can change it from function to PAR as parametric. You can actually graph curves in your calculator as well. So I made a table of values, as you can see. When t is negative 2, x is 5, and y is negative 3. I'm just plugging in those t values. When t is negative 1, you get 2 and negative 2. At 0, you get 1 and negative 1. At 1, you get 2 and 0. And at 2, you get 5 and 1. And I did that, and then I made a graph out of it. You can see I plotted all those points. Importantly, I'm only plotting the x and y values. I'm not plotting those t values. Right, the t values here are supplying me with both the x and the y coordinates. One other fun little piece of information is that we also get a direction of motion. So we can see that in this case, just with the ordered pairs that I graphed, we start down here at the bottom and we go around the curve and end up at the top, because that's the direction that our t values went, right? Negative 2 for t gave us this point all the way at the bottom. All right, so there's one example. Let me clear the board and let's do a little bit more. All right, so we're going to continue on. I have a couple of examples I want to do here with a little bit of notes in the middle. Let's look at this problem. The position pxy of a particle moving in the xy plane is given by x is equal to 3 minus 3t and y is 2t, where t is between 0 and 1. Identify the path by finding a Cartesian equation for it. So all I'm going to do is I want to take these two separate parametric equations and I want to shove them together into one equation with x and y. Basically, I want to make it look like a normal equation that we're used to seeing in the Cartesian plane. So all I did was I solved the y equation for t. So I divided both sides by 2 to get that t is equal to y over 2. I then substituted that in for t in the other equation. So x is then 3 minus 3 times, and there's my y over 2. So then with a little bit of work, I was able to get rid of the parentheses and get y by itself, so that we have a nice line in slope-intercept form. Now, importantly, it's not the entire line, right? We have a line segment here because t is only from 0 to 1. So if we wanted, we could go back and figure out what x values we're actually allowed to use. You can go back and plug in 0, and if you do that, x is 3. And if you plug in 1, you get 3 minus 3, so you get 0. So you get all the x values from 0 down to 3. This would actually be going backwards from x equals 3 to x equals 0. But there we go. All right, next up, the natural parametrization. I can talk, really. For y equals f of x. So this is just a way to take a normal function and turn it into a parametric function. So basically, all we're going to do is we're going to call x t, and y is f of t. So as an example, if f of x is x to the 5th, perfectly wonderful function of x, we're just going to call the x parameter x equals t, and the y parameter will be t to the 5th. And so we have this, and it allows us then to have a direction of motion as t goes from whatever we want. Why is that important? Well, you could use this, say, for the motion of celestial bodies, things like the Earth and, an asteroid. If you want to know if the Earth and an asteroid are going to hit each other, they not only have to occupy the same space, but they have to do it at the same time, right? It doesn't matter if that asteroid crosses the Earth's orbit when the Earth is clear on the other side of the sun. So a parametrization of the two paths would allow for us to figure out if they actually do intersect. All right, but let's go on to my last example. I'm going to slide this computer over so you can see it. There we go. So for my last example, I want to find a parametrization for the curve that is the line segment with endpoints of -1, 3, and 3, -2. So we can play around with this in a few different ways, but the easiest is to just call one of those 2 points a starting point. And to do that, let's call t 0 there. So when t is 0, x is -1 and y is 3. I'm just stealing the 2 coordinates from that ordered pair. From that, I'm able to say, well, look, this is a line segment, which means everything is linear. So x is going to be -1, and then we're going to add some multiples of t. And y will be that 3 that we start at plus something times t. And so the easiest way then to do this is to pick another t value. I chose 1 because it's easy, but it's also rather arbitrary. We could just as easily have picked 100 or 1,000 or pi. I don't know, we could pick lots of things. But I picked 1 because it's easy. So if you plug in 1 for t, you get that when t is 1, we should be at the other endpoint. Okay, again, if you picked 100, you would still want to use the other endpoint then. But so at the other endpoint, x is 3, t is 1, so I dropped out the t. And so we get 3 is -1 plus a, so then I can say that a is 4. I did the same thing for y. I used the y coordinate there, which was -2. There it is. And again, t is 1, so I get -2 is equal to 3 plus b, so b is -5. So now that I have a and b, I can go back and write my parametrization. X is that -1 we started at, plus 4 times t. Y is the 3 that we started at, minus 5t, and that's when t goes between 0 and 1. So there we go, we have the parametrization. So there you go, that is section 2.1. Have a good day.